Welcome to the next video in our series on power. Here we're going to do power for simple linear regression, and we're also going to do it for a random effects model. So you can see how to go about doing this from a pretty straightforward standpoint. Okay, so where we left off last time, if you didn't watch a previous video, you might want to jump back to it because it talks about the ideas of power. Here we're actually going to do it we're going to calculate some stuff. So first, simple linear regression. So this seems simple enough, but it's not as simple as you would think. So what we want to do is, instead of here we're going to be interested in whether the covariate matters, B1, beta 1. Does this matter? So we're going to look at the ratio of beta 1 to the noise, because beta 1 is the slope, but if there's a lot of noise estimated around it, it often is difficult to discern whether anything is significant. All right, so here's power, how we're going to do this in general, and this works just about in all cases. Generate data from the proposed model, okay? Analyze the data from the proposed model. Okay, record the p-value, determine the p-value to indicate significance, record if the test is significant. Repeat the above 1,000 times or so, determine the proportion of tests that rejected under those settings. This is the power, okay? So it's pretty straightforward, it's very formulaic, but when you do this, you should always run this under the null hypothesis first to make sure that your power is 0.05 or whatever your significance level is. So if your significance level is 0.01, then you should have a power of 0.01. All right, so let's get started. Here we're going to do this. Now, you might want to pause the video here so that you can copy this down. Okay, I'm not typing along, but here you can pause it. You see all the code here, and I'll go through and explain it, but I might move faster along than you are able to go. So I have beta 0, which I need to define. I've picked it to be 10. It really doesn't matter what it is, by the way, in this case. B1 is the thing I'm interested in, and we're going to put it at 0. That's the null hypothesis. NSAMPS is how many times I'm going to repeat this process. So, like I said, I'm going to do the whole process 1,000 times or so. Here, it's 1,000 times. Here, I'm creating a container for my results. I got a p-value 1 hold, and have a repeating vector of zeros, the length of the number of samples that I'm going to do. Okay, and for here, I don't have any real data, so my X data is going to just be uniform between 0 and 10, and N1 is the number of data points that I'm going to have. Okay, so here for I equals 1 to the number of samples, this number of samples is the number of iterations that I'm going to do that I mentioned before. It's 1,000. What we're going to do is we're going to generate Y1 is B0 plus B1 times X1, which is a simple linear regression. Then I'm going to add some noise to the end. This is that epsilon thing, okay? So here we have this epsilon idea. We're going to test the model by running a linear model. From it, we're going to take the summary, and the summary has the coefficients on it. And in the position 2, 4 in those coefficients, if you go through and look at all this, run it line by line and look at each piece, you will find that this is where the p-value for B1 is located. Okay, so then I have p-val 1 hold, and then I'm putting in here what this p-value is. And then it runs this 1,000 times, okay? It just goes crazy and runs it 1,000 times and records me 1,000 p-values. So to get the power, I say, give me the mean of if else the p-value is less than my significance level. Now, it shouldn't be 0.05 for everything, but here I'm going to use 0.05. You could be 0.01 or whatever your significance level is. Okay, now, again, you might want to pause here, finish this up, and when you're doing it, why don't you comment it? Because when you put comments in, it'll make sense later. Now, the one thing we didn't define was N1, so how many samples do you want to have? And we'll talk about that later. Okay, so if I run the code, and I think I put in here that N was, I think 20. So N1 was 20. Here I get 0.043. And this is a histogram of the p-values. I can look at that as well. And the reason I want to look at it is notice it's nice and uniform, and my red line here is where 0.05 is. And if I look at this, this is pretty close to 0.05. Under the null hypothesis, I get 0.05 or something about there which tells me that I'm doing this right. Doing this 0.05 check or whatever your significance level is really important because it lets you know if you're doing this thing right. Because if you get some weird answer, probably doing it wrong and you need to go back and debug. All right, so let's change things a little bit. So here I'm going to make B1 equal to 0.1. And here's sig2 equal to 1. Okay? Then when I run this through my looping before, all that stuff, a couple slides back, I will get out 0.137. And this is what the histogram of the p-values look like. Here's my 0.05 cutoff. So I have all of the information that I need here from this. And I can see that my power went up because I had a slight increase in the slope. So the slope is there, but it's not very strong yet. If I do 0.02, still sig2 equals 1. Run all of that again, I get 0.345. Now, remember, we're doing this via randomization, right? We're randomly generating data. So your answers might differ from mine, and they probably will. But if they, by chance, they're the same, well, great. Okay, so notice that the power is going up as we are increasing B1. Move it to 0.3. Now my power's up to 2/3 or 0.677. And notice my histogram of p-values is beginning to be more and more stacked down near the cutoff value. If I make it 0.04 or 0.4, I get 0.899. So my power is about 90%. So if there was a strength of the regression this high, given my setup, this would be the power. I'd be quite likely to find that as being significant. And if I go to 0.5, notice it's almost 1. It's really, really high here. So no, you go across a variety of values because people are going to ask what are the values and what are the powers associated with them. And you can make a plot like we did in the last video. All right, so notice I said power can be calculated by simulation for almost any situation with a model. If you don't have a model, it becomes more difficult. The hard part is generating the data from the proposed model. The remaining steps are pretty straightforward because most of the analyses are canned already in R, and you can just rely on them. As long as you can extract a p-value out for the thing you're looking for, bingo, you've got it. Okay, and again, always make sure this power is whatever your significance level is when the null hypothesis is true. Otherwise, bad things will happen. Okay, let's look at something a little more complicated. Suppose we have a simple linear regression, but we have a random effects model because the data are not independent. Okay, suppose we're repeatedly measuring a person or repeatedly measuring something. This is often when you would use a repeated measures or a random effects model. So each person has their own effect on the result across time. So I have Yij, notice I have two subscripts now, beta 0 plus beta 1. Beta 1 is what we're interested in, Xij. And then here I've got this random effect for the person. The person is adding some extra effect, either up or down. And notice that this effect, if you played around with these, is only on the intercept at this point. We could do it in interaction where it messes with the intercept and the slope, but right now it's just on the intercept, and we have some random error. Notice that this follows normal 0 sigma squared, and delta j is normal 0 tau squared. And we have this other caveat here, the covariance between these two random effects is 0. So in a sense, they're independent from each other. Okay, and here delta j is the person effect. So it's how that person is shifting that line up or down depending on their particular whatever. Okay, so let's give this a go. First, set up the parameters. Here, the library you're going to need to do this is LME4. Okay, so if you don't have it, you want to go to CRAN and download this with the install packages type idea. So you're going to get LME4, download it, and then run this library statement so you can use it. My N1 is 20, my tau2 is 0.5, my sig2 is 1, my B0 is 10, my B1 is 0, and R1 is the number of measurements I have on the same object. Okay, so I'm repeatedly measuring the same person objects. How many times did I do that? Now, if this varies, then everything goes out the window here. But if it doesn't vary and it's consistent, then you could just plug in this number for power, right? In the data, what comes at the end, who knows? People might drop out, quit, because they can't stand doing this anymore. All right, so again, you're probably going to want to pause the video at some point along the way here so you can comment all this down and write all this down, because you can't just copy and paste it right out of a video. It's really hard to do that. But again, we have the number of simulations that we're going to run, or samples we're going to pull, which is 1,000. So we're going to repeat this process 1,000 times. I have a container here that has zeros in it for the number of simulations I'm going to do. These are often called Monte Carlo simulations. That's why it's simulation. For j equals to 1 to the number of simulations, here I have an output. So I've got x1, y1, and I have subject, because in order to use the program, I need to have these variables. And so this is a container that helps me hold places for my data, because I'm going to generate it. Okay, so here's where I generate the data. So here, x1 is random uniform. How many of them? R1. Remember, R1 is the number of observations per person, and this goes from 0 to 10. We're just randomly pulling them. Delta 1, okay, is this person's random effect. So we're going to pull one of them. Notice this is N1, so how many people we have. Pull one of them. This is their individual effect, okay, with a mean of 0 and a standard deviation of tau 2. Y1 then becomes B0 plus B1 times X1, just like in simple linear regression, but then we add in this delta 1. So their individual random effect and the random noise, the epsilon that's on the end, and there are R1 of these, because that's how many times we repeatedly measured them. Then we're going to store this away, so X1 is going to get stored in X1, Y1 with Y1, and subject is equal to I. Okay, and then we're going to R bind them together, so we're going to stack them up. So R bind will cause them to stack. We're going to run the full model, which is using LMER, and this is the code, Y1 tilde X1, plus a random effect for subject, and my data is out 1. Then I'm going to run a reduced model. So R1 here, LMER, Y1, plus 1 given the subject. So this is just going to have a random intercept for each subject. Okay, so this is testing whether or not they differ at all. Okay, and then here A1 is doing an ANOVA test between the two. And then we can pull off the probability of a chi-squared with bracket 2 here, which is the p-value. So this is going to do a chi-squared test on a likelihood ratio test for these, because these are not your standard models, and we're going to store it off. Okay, so this is kind of busy. So there's other ways you can play with this, like you could put a 1 here as well, 1 plus. But right now we're going to leave it at this. So this produces the following histogram. If beta 1 is 0, I get this histogram. This is my power, 0.058, which is pretty close to 0.05, so I'm not really worried about it. If I wanted it to be closer, I can run more simulations. But if you're following along with this and actually running them, you can see this is not instantaneous. It doesn't like you hit it and the number pops out. You actually have to wait a minute. All right, so let's increase the actual slope and see what happens. Oh, wait, this is where I've purposely have this set up to where you can do this. If you understood what we did before, you should be able to go through exactly the same idea with B1 and see how strong the slope needs to be in order for it to be statistically significant with a power of at least 0.9. So I want you to go through and hunt this down. You have all the tools. You just need to follow through and knock this out. It's not that hard, but it is sort of how you do things. If you're a statistician or a data scientist, you are going to be doing this quite often, and they're going to want to get a power of 0.9, and you need to tell them how big of an effect size they can see. Now, if you really want to have some fun with this, pick the effect size that they want and see what size sample they need in order to get that. Okay, so this has covered this part of power, and we'll see you in the next video.